Okay. So what we're trying to do is come up with angle, sum, and difference formulas. The derivation I'm going to do right now is not something I'd expect you to be able to reproduce. So if you just kind of want to sit and watch, that's fine. The goal here is for like understanding. There's kind of quite a bit of like detail that's going into this that I would not expect you to be able to reproduce. But kind of the general idea I would expect you to understand. Okay? So let's say we have two angles. I'm going to call this first angle, angle V. And then I'm going to call this other angle here, angle U. And then I'm going to call this angle right here, theta. What is the relationship between angle UV and theta? What kind of relationship can I draw between those three angles? What was that, Mark? Excellent. Everybody agree with that? So that's what I'm going to be using. What I want to do is I want to evaluate like either the sine or the cosine of this theta. Okay. So to do that, I'm just going to imagine theta in the first quadrant. Why is it okay for me to just imagine theta in the first quadrant like this? Have I changed the size of the angle by just picking up and moving it? No, right? So everything is fine, right? Okay. So what I'm going to do now is I'm going to assign some coordinates based on the unit circle. So this angle here, if that's a point on the unit circle, what would the x-coordinate be for this point? It's cosine of v, comma, sine of v, right? For the sake of argument, I'm going to call that point B. What would if I call this point A, what would the coordinate be for A? It would be cosine of u, comma, sine of u. Right? Can everybody see that? Those are points on the unit circle. That's how we evaluate an angle, right? Is it's the sine and cosine are the coordinates on the unit circle. Similarly over here, this point would be 1, 0. I'm going to call this point B prime. And then this point I'll call A prime would be cosine theta, comma, sine theta. Everybody so far so good with the construction we've done here? Now what I want to do is I want to talk about this length here. So that segment. What can I say about the length of those two segments? What do they have to be? They have to be the same, right? Everybody agree with that? If that's the same angle theta, and the distance from the origin of each of those points is 1 unit, then that length of that angle or that segment has to be the same. So I can say that AB is equal to A prime B prime. Here I'm using the notation for the length of a segment from geometry. Remember that? So that's what the AB is in A prime B prime. Back from geometry, how did we calculate the length of a segment like that? We had a formula to do this. Does anybody remember what it was called? It has a very common-sensey name. Starts with a D. The distance formula. Does anybody remember the equation for the distance formula?
X1 minus Y1 squared plus
It's the square root of x2 minus x1 squared plus y2 minus y1 squared. What is it basically the same as? The Pythagorean theorem, right? Okay. So if I apply the distance formula, stop talking please, to these points, so that's going to be what we have, right? So we're going to now start trying to simplify this down. Okay? What's the first thing I can do to simplify this down? How about I square both sides? What is squaring both sides going to do? Yeah, it's going to get rid of those square roots, right? Okay, that's the first thing we should do. And then somebody said to expand. Let's do that next. Okay, so when I do that, I'm going to get cosine squared v minus 2 cosine v times cosine u plus cosine squared u plus sine squared v minus 2 sine v sine u plus sine squared u equals, and then I'm going to just write this on the next line, 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta. Everybody okay that I just multiplied that all out? Okay. Now let's look for things to cancel, or that we can simplify anyways. Well, if I look here, I have a cosine v, or a cosine squared v, and a sine squared v. That's one. I have a cosine squared u and a sine squared u. That's another one, right? So I'm just going to write that as 1 plus 1, or I'm just going to write 2 here. Everybody's good with that? Okay. So that's all the simplifying I can do on the left-hand side. If I look at the right-hand side, though, I have another one. So again, I have a 1 and a plus 1, so I'll make that just a 2. Everybody happy with that? Okay. What do you want to do next? How about we subtract 2 from both sides? What's that going to do? Get rid of those, right? Okay. What else can we do? How about we divide both sides by -2, right? That'll just clean things up a little bit. Okay. Oh, great. Because what are we trying to get? An expression for v plus, or cosine sine, whatever, of u plus v, right?
Yeah.
Or u minus v, I guess, in this case. And what did we say theta was? I think it was u minus v, though. So we have now our identity.
Now that's what I want.
Okay. Everybody's okay with what we did there. So that's our first identity. We're not going to derive any more of the identities. We're going to build them out of this one. It's going to be fun. So what if I want cosine of u plus v now? So Miguel says I need to make it a negative. So a plus is the same thing as minus a negative, right?
Yeah.
Everybody agree with that? So if I plug this in, then I'd have cosine of -v times cosine u plus sine of -v times sine of u. Now, if I think to my odd-even identities, what's cosine of a -v?
Just cosine.
It's just cosine. And what's sine of a -v? No, negative sine. So what we can do then is we can collapse this down and say then that cosine of u plus v is equal to cosine v times cosine u minus sine v times sine u. Now, typically, we're going to combine these two statements together and write them as a single formula because, well, we're mathematicians and we're lazy and we don't want to write more than we have to. So usually we're going to write it, or typically we're going to write these two equations combined into one statement. In this fashion. So the way we read this formula, stop talking please. Yep. Exactly right. So Miguel says the way we read this is if we're doing an addition problem, we use the subtraction. And if we're doing the subtraction problem, we do the addition. Right? So whatever's on top, we do together. What's on bottom, we do together. And that's the way that would look on your identity sheet. Would be like this. Okay? So what can we do with this? So we can do things like find the exact value of cosine of 75. Notice here, if we wanted exact values, typically what are we going to have to use? The unit circle. Is 75 degrees a unit circle angle? No. However, maybe I can write that as the sum or difference of two unit circle angles. What was that, Miguel? I think you had it. No? 30 plus 45, right? That gives us 75. Those are both unit circle angles. Everybody okay with that idea? So 30 is like my U, and 45 is like my V. So I just plug them into the formula above. So I have cosine of 30 times cosine of 45 minus sine of 30 times sine of 45. And then I just go to my unit circle. So if I look at my unit circle, cosine of 30 degrees is square root 3 over 2. Cosine of 45 is square root 2 over 2. Sine of 30 is 1/2. And sine of 45 is square root 2 over 2. So when I multiply these together, I get square root 6 over 4 minus square root 2 over 4. So I can write that as the single fraction square root 6 minus square root 2 all over 4. So one of these things, these identities are going to allow me to do is to find exact angles or exact values of sine, cosine, tangent of angles that I couldn't do before. Mark, you have a question? Okay, you just looked puzzled there for a minute. Okay. Everybody happy with that? So the trick here is just finding the two angles that you can add or subtract, right? Could you have done this as a subtraction problem? Yup. Yeah, definitely super slab, right? So you could have done like 135 minus 60, right? That would have also worked. So it doesn't really matter whether you want to do it as a sum or difference. Everybody okay with that? All right. So what if we want then, say, to figure out some things for sine? So here we're going to choose theta to be u plus v. So sine of theta, or sine of u plus v, then is just going to be sine theta, right? That's kind of a dir. Why did I write it this? Why did I want to write it this way? Because I'm going to use the cofunction identity now to write this as cosine of pi over 2 minus theta. And since theta is just u plus v, I can distribute the negative. What's up? Square root 6 minus square root 2 over 4?
Yeah.
So I can distribute the negative through there. And now I'm going to regroup this, because I want to get the u's and the v's in separate parts when I apply the cosine different, or the angle difference formula for cosine. So this part now is like my u, and this part is like my v, using the angle difference formula for cosine. So I'm going to use the formula that I just made to do this. So that's going to be cosine of u times cosine of v plus sine of u times sine of v. Now cosine of pi over 2 minus u, I'm going to use my cofunction identity, and that's going to turn into sine of u. Similarly, for sine of pi over 2 minus u, I'm again going to use my cofunction identity. That's going to turn in cosine of u. And so we have sine of u plus v is this. Okay. What if I wanted to do the subtraction? Well, I'm going to use the same trick I used before. I'm going to think about sine of u minus v as sine of u plus a negative v, and use the formula from above. So that's going to be sine u cosine negative v plus cosine u sine negative v. And if I use my odd-even identities, cosine of negative v is cosine of v, and sine of negative v is negative sine v. So I'll just put the negative out front and turn into a subtraction problem. And I'm done with that one. Well, because I have it in terms of just u's and v's, right? That's what I want. So again, we'd combine these typically when we write our formula. Make sure I write this in the same way I did on here. With a plus minus. Oops. Make sure I write it the correct way. So that's the way when we combine those two identities into a single. Everybody okay with that? And let's do one more. And luckily, this one is the easiest one. Because what is tangent? Sine over cosine. So if I apply my identity for sine, I get this. And I apply my identity for cosine, I get this. But this is a little bit unsatisfying because we have tangent of an angle sum or difference expressed in terms of sines and cosines, right? I'd rather have that expressed in terms of tangents. So here's my trick. I'm going to multiply the top and bottom by 1 over cosine u times cosine v. And it's okay to do this because I'm really just multiplying by 1, right? Because I'm doing the same thing on top and bottom. So if I do that, when I distribute to this first piece, the cosine v's are going to cancel, and I'm left with sine u over cosine u, which is just tangent u. When I distribute to this piece, the cosine u's are canceled, and I'm left with sine v over cosine v, which is just tangent v. When I distribute to the denominator, cosine u's cancel, cosine v cancels, and I'm left with 1. And when I multiply to this term, I get sine u over cosine u times sine v over cosine v. So just tangent u times tangent v. And this is the form that you'd be a little bit easier to deal with and more likely to see. This is the form on your identity sheet. Okay? So those are the 3 angle sum and difference identities. That's all we're going to worry about here in the first section, are these 3 identities. Let's do some examples of problems we can ask you to, some more problems we can ask you to do using these identities though. Okay? So the problems that we're going to look at now, each of them, your main tool is going to be using one of these 3 identities. Okay? So let's say I want to find sine of 5 pi over 12. Okay, so we're going to use one of the angle sum or difference equations to do this, right? Now this is a little bit less intuitive because we've written these angle in radians, right? If I go and I look at the angles on my unit circle, they are in 1/6, 1/4, and 1/3 of pies, right? Everybody agree with that? So I want to write this as something over 12, and I'll just say for the sake of argument, let's do it as a minus. But I need the numerator to reduce down so that these things are like a 1/4, a 1/3, or a 1/6, right? So give me an example of 2 numbers that I can subtract to get 5. 6 minus 1. If I do that, though, this one doesn't reduce down to a 1/3, a 1/4, or a 1/6, right? So 8 minus 3. If I do that, 8/3 reduces to 2 pi over 3. And 3/12 pi reduces to pi over 4. Those are both unit circle values. Okay, so it's just about picking the right difference there. And it should be, as long as you get them to reduce down so that they're either 1/3, 4ths, or 6ths, you're fine. Okay? So if then I apply my formula, I can say I have sine of 2/3 pi times cosine of pi over 4 minus sine of, or I guess I'll write in the same order they do, cosine of 2 pi over 3 times sine of pi over 4. And then if I go to my unit circle, sine of 2 pi over 3 is root 3 over 2. Cosine of pi over 4 is square root 2 over 2. Cosine of 2 pi over 3 is a half. And sine of pi over 4 is square root 2 over 2. So we get the same thing that we got before, square root 6 minus square root 2 all over 4. Everybody okay with that? So again, don't let the fractions scare you, right? You just have to pick the numerator so that things will reduce down into either thirds, fourths, or sixths of power. That's all you need to worry about. Okay? Yes, of course. So this one says to write this as a single trig function. How am I going to do this? I'm just going to look for the identity that whose right-hand side looks like this. JJ? Sure. If I do that, this looks like the difference formula for sine, right? Where this is like my u and my v. So this is just going to equal sine of 47 minus 23, or just sine of 24. And I'm done. Look at the difference formula for sine if you don't see exactly what we did. Because the difference formula for sine is sine of u times cosine of v minus cosine of u times sine of v, right? So that is exactly what we have here. And so it just simplifies down, like one little step, easy peasy. Okay. Okay. So the next one, we're going to prove this identity. So cosine 3x plus cosine x equals 2 times cosine 2x times cosine x. Which side would you want to work on here? I would not work on the right side. I would work on the left. The reason I'd work on the left is the 3x, the side with the bigger coefficient, is usually going to be the place where you're going to want to start. So the first thing that I'm going to do is I need to get rid of that 3x there. So the way I'm going to do that is I'm going to think about that as cosine of 2x plus x. Everybody okay with that? Okay. I'm now going to apply my angle sum formula for cosine. So this is like my u and that's like my v. So I have cosine of u times cosine of v plus, minus sine of u times sine of v. And then I still have that cosine x floating around there. Are we okay with that? Okay. Oh, that should be an X. My apologies. Okay. Now, here is the sneaky piece. You ready to get sneaky? Okay. Watch what I'm going to do now. I'm going to rewrite this as an angle difference. How can I rewrite that as the difference? I can write that as 2x minus x, right? Oh, let's pause for a second. Why am I doing this instead of working on the other parts? Because I'm doing this and you don't understand why I chose to do this. Notice that piece that I'm trying to get to on the right-hand side. I have one of those already. Everybody agree with that? I need to get a second one of those. The way I'm going to, and I shouldn't get any cosine there flapping around at the end, right? So that was my cue, like I need to do something to this cosine to get it out of there. I'm going to use this angle difference formula to accomplish that. Does that make sense now on what I saw? Okay. Because that's the important part, right? Like, if you don't see the same thing that I see, fat lot of good this does, right? So when I apply the cosine angle difference formula, I get cosine of 2x times cosine x plus sine 2x cosine, or I'm sorry, sine x. Yeah, it gets a little long, but it's not that big of a deal. Because look at what happens now. And then, like terms. So right when it started to get really gross, everything kind of collapsed down and came together, and we got exactly what we need. Yes, of course. We're going to stop here. Sure, why not?